Picture this. It's the late 1800s, and the world is experiencing a transportation revolution. Steam engines have conquered the railways, bicycles are transforming personal mobility, and now 3 inventors on different continents share the same audacious dream. They want to make ships that roll across the ocean on giant wheels like massive aquatic automobiles. This is the forgotten story of the roller ships, one of history's most spectacular engineering failures that teaches us why sometimes the most obvious ideas are actually impossible. Our story begins in Victorian England, where a mysterious inventor named Robert Fryer has been working in secret for 12 years. Since 1868, he's been obsessed with a radical idea. If wheels work so well on land, why not use them on water? By 1880, Fryer has spent £14,000, a fortune worth about £1.5 million today, building something he calls Alice. Imagine a triangular platform floating on 3 massive paddle wheels, each 20 feet across. The wheels don't just float, they're supposed to propel the vessel forward using bucket-like paddles. Fryer believes Alice can crawl out of the water and continue rolling on land, making it the world's first amphibious vehicle. The reality proves crushing. When Fryer fires up Alice's steam engines, the vessel barely moves. The paddle wheels churn water into foam, creating more turbulence than thrust. Each wheel interferes with the others. After months of failed trials, with Alice barely achieving walking speed and proving impossible to steer, Fryer admits defeat. His vessel is broken up for scrap. You'd think this failure would discourage others, but it inspires them. Fast forward to 1891 in France. Ernest Bazin, a distinguished civil engineer and former merchant marine captain, believes he can succeed where Fryer failed. Bazin isn't some amateur inventor. He's a graduate of the prestigious École Centrale des Arts et Manufactures, with successful inventions in canal locks and harbor construction. He's convinced that conventional ships have reached their speed limit. To go faster, you need to think completely differently. For 5 years, Bazin conducts methodical experiments with scale models. His conclusion is revolutionary. Instead of pushing through water like conventional ships, his vessel will roll over it on massive lens-shaped discs. The theory seems brilliant. These lenticular rollers will support the ship above the water while rotating to propel propulsion. Like a wheel rolling on pavement, they should glide through water with minimal resistance. Bazin promises investors a ship capable of 32 knots, nearly twice the speed of conventional steamers, while using only 800 tons of coal to cross the Atlantic instead of 3,000. On August 19, 1896, crowds gather at Saint-Denis near Paris to witness the launch of the Ernest Bazin. The sight is extraordinary. Picture a vessel 131 feet long, supported by 6 massive rotating discs, arranged in 3 pairs. Each disc measures 33 feet across and 10 feet thick at the center, tapering to sharp edges like a lens. The ship's platform sits 13 feet above the water, giving it the appearance of some fantastic mechanical insect. The engineering is impressive. Each pair of rollers operates independently, driven by 50 horsepower engines. A 500 horsepower auxiliary propeller provides additional thrust. The total 750 horsepower should easily achieve the promised speeds. The French press hails it as the future of ocean travel. Initial tests seem promising. The vessel floats perfectly at the predicted draft. The rollers turn smoothly when tested out of water. March 1897, the River Seine at Rouen. The moment of truth arrives as the Ernest Bazin prepares for its first real test. The engines roar to life, the massive discs begin rotating, and then disaster strikes. As the rollers turn through the water, something unexpected happens. The water doesn't slide smoothly past the rotating surfaces. Instead, it clings to them with stunning tenacity. Witnesses describe an incredible sight: waterfalls cascading from each roller as they emerge from the river. The water adheres to the surface through viscosity and surface tension, creating what one engineer calls 6 continuous water breaks. The faster the rollers spin, the more water they lift and the more power they consume. It's like trying to run while carrying increasingly heavy buckets of water. The physics are merciless. At maximum engine power, the Ernest Basin achieves only 7 to 8 knots, less than half the minimum predicted speed, while burning fuel at twice the expected rate. The steering system, which relies on varying roller speeds, creates unpredictable yawing movements. The auxiliary propeller churns uselessly in the turbulent wake of the rollers. Vibrations from the struggling machinery shake the entire platform. Basin refuses to give up. For 9 months, he experiments desperately. He tries different surface textures on the rollers. He adds devices to scrape water from the ascending surfaces. He experiments with various coatings to reduce water adhesion. He adjusts rotation speeds, modifies gear ratios, rebuilds transmissions. Nothing works. The fundamental physics remain insurmountable. On January 21, 1898, Ernest Basin dies suddenly, just weeks after claiming he had finally solved the water adhesion problem. His secrets, if they existed, die with him. The Ernest Basin continues operating briefly for demonstrations, even visiting England. But by 1900, the dream is dead. The vessel is sold to a scrap dealer in Preston, England. Its massive rollers cut up for their metal value. Meanwhile, across the Atlantic in Canada, an even more audacious experiment is underway. Frederick Augustus Knapp, a lawyer from Prescott, Ontario, has no engineering training whatsoever. What he does have is remarkable vision and extraordinary powers of persuasion. His design is radically different from anything attempted before. Imagine a giant cylinder, 110 feet long and 22 feet in diameter, designed to roll across the water like a massive rolling pin. Inside this rotating outer shell, a smaller, stationary cylinder houses passengers, crew, and engines. The outer surface features spiral flanges that supposedly will pull the vessel forward, like a screw threading through water.
Knapp's ambitions are breathtaking. He claims his roller boat will achieve 60 miles per hour, making it the fastest vessel on water. He produces elaborate drawings of 800-foot ocean liner versions capable of carrying 30,000 troops or 240 million pounds of grain. Most audaciously, he hopes to transport Queen Victoria herself, who notoriously suffers from seasickness. The non-rotating inner cabin, he promises, will eliminate all motion sickness. The construction at Polson Iron Works in Toronto is an engineering marvel. The stationary inner cabin connects to the rotating outer hull through an elaborate bearing system that would challenge modern engineers. Steam engines inside the cabin drive gear trains that engage rails on the inner surface of the outer cylinder. The mechanical complexity is staggering. On September 8, 1897, thousands gather on Toronto's waterfront. Investors from Montreal, Quebec City, Chicago, and even British interests have contributed $125,000, a massive sum for the era. The crowds watch in amazement as the giant cylinder enters the water, its polished surface gleaming in the sun. The trials quickly reveal the same merciless physics that doomed Basin. The rotating cylinder creates enormous drag, far exceeding any forward thrust generated by the spiral flanges. Maximum speed, 3 to 5 knots. Steering is impossible. The cylinder simply goes wherever currents and wind push it. The bearing system between inner and outer cylinders, despite careful engineering, creates friction that absorbs much of the engine power. Waves cause the cylinder to pitch and roll unpredictably, making the supposedly stable inner cabin a nauseating torture chamber. The maiden voyage from Toronto to Prescott on June 9, 1899, becomes a comedy of errors. Just 25 miles out, near Pickering, the engines break down. The coal runs out. The roller boat drifts helplessly until the crew manages to tie it to a tree off Bowmanville. A second attempt ends similarly, with the vessel abandoned along the shoreline. Knapp, ever the optimist, attempts to establish a ferry service between Toronto and St. Catharines in 1901. The service lasts exactly one trip before mechanical failures force another abandonment. The roller boat spends the next decade slowly rotting in Toronto Harbor, a cylindrical monument to impossible dreams. In 1927, the city's waterfront expansion simply buries it under tons of landfill. Today, if you drive along Toronto's Gardiner Expressway near Lakeshore Boulevard, you're passing directly over Knapp's buried dream. Archaeological surveys in 2009 confirmed it's still there, waiting under the concrete like a sleeping mechanical whale. So why did all these roller ships fail so catastrophically? The answer lies in fluid dynamics that the inventors didn't understand. Water behaves nothing like solid ground. When a wheel rolls on pavement, it touches at a single point. But rotating through water, the entire submerged surface creates drag.
Water's viscosity causes it to stick to moving surfaces, creating a boundary layer that gets carried upward against gravity. Surface tension creates sheets of water that cling to ascending surfaces. The rollers become giant water wheels running in reverse, lifting tons of liquid with every rotation. The power required increases with the cube of velocity, making high speeds impossible. The rotating wheels also create chaotic turbulence that increases total resistance. Despite these well-documented failures, the roller ship concept refused to die completely. In the 1930s, during the great age of streamlined design, magazines like Modern Mechanics and Popular Science featured fantastic wheeled vessels. Artists imagined massive ocean liners rolling on 200-foot wheels, or sleek yachts skating across the waves on multiple rollers. These remained safely on paper, their designers perhaps learning from history. As recently as 2015, naval architecture students at MIT used advanced computational fluid dynamics to model Bazine's design. Their computers confirmed what 19th-century physics couldn't fully explain. Achieving Bazine's predicted speeds would have required approximately 5,000 horsepower, far beyond any steam engine of his era. Even with modern materials and engines, the fundamental efficiency would remain terrible. Yet, these spectacular failures weren't without value. They contributed crucial lessons to naval architecture. They demonstrated the vital importance of understanding scaling effects when extrapolating from models to full-sized vessels. They helped establish experimental protocols still used today. The detailed documentation of failure modes advanced early understanding of fluid structure interaction. The willingness of investors to fund such radical concepts helped establish a culture of maritime innovation. Perhaps most importantly, the roller ships became standard case studies in engineering education. They teach future naval architects the crucial importance of understanding fundamental physics before pursuing radical innovations. They demonstrate that enthusiasm and investment cannot overcome the laws of nature. The roller ship story occurred at a unique moment in history. The 1880s and 1890s were a time of unprecedented technological optimism. Steam power had transformed civilization. In this atmosphere, making ships that rolled on wheels seemed no more impossible than any other miracle of the age. Today, as we develop new technologies, the roller ships remind us of essential truths. Bold vision must be tempered with rigorous science. The most obvious solution isn't always the right one. And sometimes spectacular failures teach us more than modest successes. The next time you watch a modern hydrofoil rise above the waves or see a hovercraft glide between sea and land, remember the roller ships. They tried to solve the same problem, but chose an impossible solution. Their failure helped point the way toward what actually works. These ghost ships of impossible dreams remind us that progress isn't a straight line. It's a winding path marked by spectacular failures that teach us the boundaries of the possible. The roller ships failed, but in failing, they helped chart the course for every successful innovation that followed. Sometimes the best way to find the right answer is to prove, conclusively and expensively, what doesn't work. In the end, their greatest voyage was through human imagination, where even failures can light the way forward.